Okay, we're going to start with the problem set on pH and pOH continued. We did a little on that sheet in both classes. I'm going to start with question number 2. I think we got to this in third period, but not in first period. So this is asking for pH, and it gives us 0.0010 molar NaOH. NaOH, as you will recall, is a strong base. Strong base means that it completely dissociates in water. It splits off. This splits right down. Hydroxide goes and does its own thing. Sodium goes and does its own thing. So this 0.001 molar sodium hydroxide is the same as saying we have 0.001 molar concentration of hydroxide. So what can we figure out from that? Well, if we've got the concentration of hydroxide, we can figure out the pOH using our formula negative log of the concentration of OH. And if we do that, we've got the negative log of 0.001. I'm not going to do all the work for you here. I will walk you through it. But if you do that, you'll find out that your pOH equals 3. So if my pOH equals 3, we're being asked for the pH. The pH plus your pOH always equals 14. So just solving this, we get our pH equals 11. 11 is the correct answer for number 2. Number 3. 3 is a bit of a weirder question. Let me get my pencil working here again. For some reason, it doesn't like to work all the time. Number 3 then. Oh, we'll do it in red. I've got a 0.05 molar concentration of Ca. Let's make my C look like a C. OH. Of course, the correct formula is CaOH2. This is a strong base, so that means that when I put this in water, the calcium goes one way and the hydroxide goes another way. But look at that. I've got 2 hydroxides, so I've got OH and OH going off their own way. So if my concentration of calcium hydroxide is 0.05, then my concentration of hydroxide ions is twice that 0.05. So 2 times 0.05 equals 0.1 molar concentration of OH. So 0.1 molar is my concentration of OH. And so to figure that out then, I just run that up the old formula. pOH equals negative log of 0.1. Negative log of 0.1 equals, that's 10 to the minus 1. So our negative log of that equals 1. So we got a pOH of 1. We're asked for pH. 14 equals pH plus 1. Our pH equals 13. Easy enough. All right, on to number 4. So what have we got going on with number 4? There we go. We've got 0.03 molar hydrobromic acid. This is a strong acid. Hydrobromic is one of the strong acids, so we can assume 100% dissociation. That means everything's going to fall apart. So my 0.03 molar is my concentration of hydrobromic acid. It is also my hydrogen ion concentration. When my hydrobromine or hydrogen bromide splits apart and hydrogen goes its own way, there will be 1 hydrogen for every hydrogen bromide molecule that we got. 1 hydrogen will split off. So, simple. Find the pH of this. pH equals negative log of my hydrogen ion concentration, which is 0.03. Run that through your calculator. You should get a pH of 1.52. There we go. Number 5. We've got 0.150 molar pOH, potassium hydroxide. That is a strong base. Why? Because potassium is in group 1. Anything that's in group 1 or 2 combined with hydroxide gives you a strong base. So what this is saying, again, with our other ones that we did like this, that our concentration of hydroxide is equal to the concentration of our stuff, our potassium hydroxide, which is 0.150 molar. We want the pH. We've got the hydrogen ion or hydroxide concentration. So what we can figure out here, of course, is the pOH. That is negative log of our hydroxide concentration, which is 0.150. Run that through the calculator. We get pOH equals 0.82. That's our pOH. Our pH plus our pOH have to equal 14 to find out the pH. We just subtract 0.82 from 14 and we get 13.18. pH of that means it is a strong base. Well, yeah, it's a strong base. It's potassium hydroxide, which we just said is a strong base. With number 6, things start getting a little weird. Let's get to it. We've got a 2.0 molar solution of HC2H3O2. That right there is acetate. It's got a hydrogen tacked to the front of it, so it's an acid. Acetate, the rules say acetate would switch to acetic acid. This is acetic acid. You run into it most often as vinegar, and it's a weak acid. Weak. So when I put that in water, it means some of these hydrogens stay connected to the acetate, some, a small number, drift off by themselves. I don't have too much free hydrogen floating around. As a matter of fact, as the problem says, we're assuming a 5% dissociation. That means 5% of the hydrogen attached to acetate will split off. So, what's our hydrogen ion concentration if we've got 2 molars of a weak acid that has 5% dissociation? Well, the answer is it is 5% of 2. How do we figure out what 5% of 2 is? We turn 5% back into a decimal. 5% is 0.05. 5% or 0.05 times 2 equals 0.1. So that is our hydrogen ion concentration. Because not all of it is splitting off, we can't say our hydrogen ion concentration is 2 because some of those hydrogens stay attached to their acetate. So please do not make any jokes about holding on to your acetate at this point. So our hydrogen ion concentration now is 0.1. So we just go to our formula. pH equals negative log of our hydrogen ion concentration, which is 0.1. Negative log of 0.1 is 1. So our pH of this stuff is 1. I know what you're thinking. Wait a minute, this is a weak acid. Why does it have such a low pH? It has such a low pH because we've got a lot in there. It's 2 molars. So that's a really low pH. That means it's probably not the same pH as your stomach acid that burns your throat. This would not be a fun acid to play around with. So that's number 6. I'm going to take a break. I'm going to stop the video for this section right here. I want you to work on 7, 8, 9, and 10, at least set the problems up, and then start the next video with those 4 problems so you can work through and see how I work them through and make sure you understand what you're doing. Check the next video after you've worked through 7, 8, 9, and 10.